Okay. Hello, everyone. Good evening. Welcome to today's session. And in today's session, we'll primarily be looking at computer vision, which is a bit different to like the exercises or examples you've worked with in the past 3 weeks. So this is like a new shift, but it's an interesting shift, which you will get to enjoy hopefully towards the end and appreciate towards the end of the session, inshallah. So yeah, so we'll just get started now. So as always, we have the notebooks in which we are using, which is from Dan Bouquet. So it's like the important reference materials for this. So as always, I'll just go through the materials and discuss a few things, highlight what is important, and get few better ideas. So hopefully when you get to go through the notebook, you'll be able to understand more and get much more deeper understanding of the topics. So like we said, we'll be treating computer vision. So if you are new to the area of like machine learning, so what computer vision simply means is how your computers can see and also identify objects. So how does that happen? So as humans in general, when you look at something, you use your eyes and you have like some kind of visual perception of what you are seeing. And to some extent, it's a bit difficult for you to even understand how you see things because it just happens. You just normally see things like the way you see maybe your computer or your phone screen and you appreciate it. So except if perhaps you are in the medical field or do some kind of optics or research related to that. So, but in computer vision, we'll try to give computers ability to see, to identify and understand images. Just give me 1 minute. I'm coming. Yes, so that's what we aim to do. And in the last class, we tried to kind of introduce some bit of fundamentals with computer vision. So I'll just briefly go over it. So in the last session, if you're not here, and all of you can help me with this exercise also. So what happens is uh, we looked at the class last week on binary classification of how you could divide like objects into two categories. So we understood what was classification. And I gave this intuitive example in how you can classify things. So just quickly, just for some class exercise, can you briefly, let's see, just give me a minute, please. Yes. Yeah, so I just wanted to get the writing tool set up. So let's say we have two categories, one which is cat and another which is dog. So looking at the images by your left-hand side, can you help me like categorize this into like two categories? One, with which images you feel it's a cat or can you see as a cat and which is a dog? Can you type in the chat, please? So I just want to see your response on this. So among the images 5 to 6, so which do you think is a cat? Which are dogs? Yeah. Yeah, just feel free to type. And if you want, you can unmute your mic. Awesome. There are some response from Abubakar. Said 1, 2, 3 are cats. And another response from Khadija, which is cool. 1, 2, 3 are cats. 4 and 5 are dogs, which is super cool. Yeah, thanks so much for the kind response. So as you can see, so over the years, you built some experience to identify like cats, and thank you also, I think there's a response from Mariam. So over the years, you built like experience of identifying cats and dog internally. So based on some particular features in which you've seen about them over the years, it might be like their fur or like the shape of their face. So maybe easily looking at 1 and 2, like their cats, which is cool. So let me just mark them here. So here, based on your responses, you say 1, 2, 3, then 4 and 5. So like for 1, 2, you could easily see them, they are cats. But for 3, you can't see the face, but you could identify it from perhaps the force or the shape of the paws. So these are like features that are very distinct to a cat. So you have seen them over the years and you've gotten to understand them, but you want to then when you look at 4 and 5, 5, it's easy to kind of identify it's a dog. But when you look at 4, it has like this eyeglasses. So let's say with the eyeglasses, if you haven't had much of experience with dogs, you might have some doubts, but you've built over the years like some knowledge about like dogs, how they look like. So even with the glasses, you can easily identify it's a dog, which is like super cool. So this particular ability that you have to identify images, we want to give it to computers. How can computers identify this when they see images or anything like this? Even though it's like totally obscure, they can be able to identify this and able to like work well with this. So these are like one of the key things we'll be discussing in this particular course. So just give me a minute. Yeah, thanks so much for your kind responses. Yeah, so I think it also raises the question, how does like a computer see images, or how can we give the computer ability to understand images? So like we said, when you look at an image, so what you just see is like just the image itself, and your brain just works out everything you need. But how can we make this task easy for computers? So looking at this image, how can we kind of transform this image into what the computer understands? So in our very first lecture, or the second one, so I kind of told you about how in machine learning and deep learning, so all your computer models see, or all your computer understands, are numbers. So when you give this image, perhaps it's in a JPG format or in any format it will be. So you want to translate this into numbers so that your computer will see and understand it and process it. So what you can do is, so with anything with images, it's divided into pixels, and each pixels is, so we can, for simplicity, it's much more like granular than this. So you can take each of these as pixels, for instance. So we can say this is perhaps, let's see, 1 pixel here. This is maybe another pixel here and several pixels, but it's much more smaller than this. But this is just for simplicity. So each of these pixels here will perhaps hold a number, maybe let's say 128. And this is maybe 0. And so in normal convention, you have 0 to, let's say, 255. So here it's like completely black. Then here you have light, maybe white. So you have this kind of wide spectrum here. So with this kind of notation, with the pixel notation, you can transform any image to a number. So it can be a very large number, depending on the size of the image and the number of channels. So when you have that number, so you can convert it into a tensor. So with deep learning, we are using PyTorch. So everything we need to be in a tensor. So all these numbers here, or each number of the pixels here, it becomes a tensor. And what we have, we could pass this set of numbers into your model. So you remember when we did the regression, so you have your X and Y, and your X and Y kind of goes into your model, and your model does some kind of prediction. But here in computer vision, it's a bit different. So instead of your X and your Y, so okay, I'm coming, let me just mute everyone. Yes. So instead of your X and your Y coming to your model here, so what will be coming into your model here are this array of pixels. So will be like your input here into your model, and your model does some prediction from that. So that's how like the summary of computer vision. Your model sees an image, so it can be extended to videos, because video is like an extended image. It's like image across time. So you have like several stacks of images across time. And with that, your image learns from those videos. So in computer vision, your model sees an image, and that image has been converted to numbers. And because easily your computer understands numbers, only numbers. So when you give it an image, it doesn't understand that. You have to convert it to numbers, and it manipulates those numbers to see what it can intelligently predict from how you've trained it. So that's like the summary. Then we'll go much more into like the technical concepts, and you get to see how it works. But feel free to ask any questions along the way. Happy to answer them. So I'll just clear this. So yeah. So 1 minute, I think I forgot something. Yeah. So so they are like common computer vision tasks, but for this particular notebook, we'll be dealing with classification. So as we explained, we are trying to identify which category each item is. So one example is like between cat and dogs, you see an image. So where does it lie? Where can we categorize that image? So here we can see a dog, so it can be either cat or dog. So this is like binary classification, which we talked about last week. So it can have like multi-level classification. So one other common computer vision task is what we call object detection. So what you do in object detection, you identify the location, you identify the object. So here you can see it's a cat, and you have like this kind of box. Your model learns to draw this box around that image, and it identifies the location in space where that object is. So it helps a lot. So one important place this is helpful is, let's see, where you have a robot that's trying to pick, or a robot that's trying to harvest food for you, and it has a camera. So with that camera, it can easily like identify where the location of that food is, and if it has like some kind of grapper, it can just go in space and pick that object from space. So this is where it's like an example of where it's important. So another important task with computer vision, which will help with segmentation. So when your model sees an image, so you can train it in such a way it can perhaps learn to like directly identify like this car over here, and perhaps and can tell this is a car, and identify this person here to as a very good accuracy as possible. So this is helpful in like security systems where you want to identify who's coming in, who's going out, or what objects they are coming in. So these are like just some common tasks you could use computer vision for. But for our own notebook, we'll just start with classification, and hopefully towards the end of the course, you have gotten substantial knowledge to extend based on what we have discussed here. So, but okay, feel free to ask any question if there are any, but we'll just get started with more of the technical aspects of it. Give me a minute. So as always, we'll be using PyTorch. So as I said, I'll be skipping some stuff that might not be important or things we've covered before, so that we can cover more ground and explain as much as possible at the end of the day. So we import the important libraries we need. So we are using PyTorch for this particular notebook. So we import Torch. And what is new here? So we've used Torch before. So what is new here is called Torch Vision. So with Torch Vision, it's a library for performing computer vision tasks that is built on Torch, that is built based on Torch. So it has like some important APIs in which you can call that helps you with this particular task, so that you don't need to build things over and over again. So they are like standard tools or frameworks or methods that have been built for you within this Torch library, which you will use over and over again. So one of which is datasets. So these datasets primarily has some kind of cluster of datasets, like commonly available datasets, which we will be using, which is FashionMNIST. If you've not come across it, you will get to see it in details, and we'll discuss it, and some other like key components. So we'll just import them now and get running. So the others are Matplotlib. I'm sure you've come across them for plotting. So as always, so this is the data set we'll be using. So what we want to do, we call it FashionMNIST. So it's a data set of images. So what we want to do is to build a model that learns to identify each of the image and classify it. So it has like 10 classes. So what happens, so since it has 10 classes, we'll say it's a multi-class classification. And since it's more than 2, if it's 2 classes, it has binary classification. So it contains several items, which we'll see in a detail. So as always in our machine learning pipeline, so first we need to get the data, then build a model and try to feed that model to our data, then see how it is performing. Then at the end of the day, if it performs well, then you save your model for later use. So yes. So right now, the very first thing we'll try to do is get our data sets. So remember, this is from Torch Vision, and we are calling FashionMNIST. So what we wanted to do is to download the data set for us if we don't have it before. That's why we set it to true here. Then we set our train. So what we are telling this particular method to do is, or this particular class to do, is download the data set, and it should be a trained data set. So we want the trained data set, which will be stored at root here. So once I run this, you will see where it is stored, and we'll be able to maybe visualize a bit and see how it is. So that's for this particular first line of the code. The second line is exactly similar. We are calling from the datasets module, we are calling the FashionMNIST class, which we want to get the test datasets. Then we specify, is it train or test? So once we set it to false, what we're indicating, we want the test dataset. Because remember, in machine learning, you have the train set and your test set. You train your model on the train dataset, and you evaluate to see the performance of the model and how your model is performing on the test set. So yeah, we'll just run this and see. So there are several other data sets like FashionMNIST, and you can check the, let me see, Torch dataset. So easily, once you see a method and you want to explore more, you can easily Google it, and you can see, so you can see this is Cypher 10, which is like objects, or yeah, common objects. These are like 10 categories. Then Cypher 100 have much more elaborate objects in which you could use. There are like several other items. So this is FashionMNIST, and this is ImageNet, one of the most popular computer vision data sets. That's before large language models. So it was used for benchmarking like really good models and seeing how well they perform. So you can like check that when you are free or something. Yes. So as you can see, we've downloaded our data, and you can easily check if you're using Colab. You can see it's downloaded to under the data repository we've set all along here. And you can see we have this. So, and yeah, so these are like, you can see this is like the train, and this is for the test. So not to just to move forward, but feel free to ask any question. I think there's a question on the chat. So there's a question from Bello. Is there a specific number for white and black? I guess this relates to the question of like pixels. I would say it depends on, so like the common classification system is like 0 to 255. When you have 0, it's like no value, that's black, and 255 is white. So you have like a spectrum. So in between you have, it's like maybe between darkness and light. So like 0 is like total darkness, and 255 is like complete light. So in between you have like something like a gray color. So you come to see it's, because here it's just a simple sense in when you're dealing with gray images, but when you see colored images, so it's like varies a lot where you talk about RGB, but don't worry, we'll look into that a bit. So can't we split here? So the idea, so Bello is asking, can't we split in this particular form? So if you remember in machine learning, so you kind of split your data. So in deep learning, you can do the same, but this is not the right step to do it. So what you're doing here is just downloading the data, but you come to see quickly on the next steps where you get to split. So here you're almost like splitting your data, because here you have the train and this is your test set. So you've almost like split the data. So, but if you want to do any further splitting, so there are sub attributes of this module here that allows you to directly split from here. But here it's already splitted for you. You have the train data and the test data. I'll quickly go next. So here is just trying to see what's there, what's in the image, and what's the shape. So as you can see here, the image shape here is 1 by 28 by 28. Remember when I showed the image and I kind of broke it down into pixels? So what this is telling you is we have an image of this form. Maybe think about it like the number of rows here are 28, then the number of columns here are 28. So that's what it's telling you, like 28 by 28. So it can be bigger than that, because this image is like low resolution image. So that's why it's 28 by 28. And for higher resolution image, numbers go like quite higher. And what this one is signifying to you, it's what we call a grayscale image, which you will see just below, like here in the bottom left. So it's like black and white, so not much of color. So that's what we call grayscale image. But in common images, like let's see how you see me now, it's like colored image. So it has color. So this number of channels will change. So typically you want to have like RGB channels. And this R just means this is the red channel. This is like the green channel. And this is the blue channel. So it helps you have like some color perception of the image. So don't worry, we'll come to see that. Don't too bother much about that. Yeah. So, but if there's anything that's not clear, feel free to ask questions. Yeah. So here we just want to get some numbers of what is the size of the training set and the test set. So as you can see, we have 60K images for the training set, which is quite good. And we have for the test set 10K images. So it's always good to see the classes available. And here, as you can see, like these are like classes. We have t-shirt, trousers, including bags and boots. And let's visualize the data set. So I'll just skip a few things. These are things you will see while running the notebook so that I focus on what's more important. So this is like the visualized image of the ankle boat, which exists in the data set. So as you can see, it's like low resolution. So for us, like it might be difficult for us to identify. Okay, don't worry, I'll talk about this in a bit. Yeah, so these are like a set of the images. So just looking at this now, you can see like for you, you can a bit of identify it, but not as much as like the earlier images of the cat and dog. So it gets more difficult. But our computer vision model in which we build will get to understand this better. So that's like the advantage of like computer vision. So it helps to understand the underlying patterns within each of the images and predict them much better. Yeah, so yes, so we've downloaded our data. The next step is to prepare what we call like a data loader. So with your machine learning models that we have, just 1 minute. Yeah, I'll explain this in a bit. So the thing is, let's say you have some huge data sets. Let's say you have some maybe data sets, very large. Let's say you have some data sets here. So, and you have your model here. So typically what you will do is like from your data set, you pass it to your model and your model will learn to do predictions. But this is a bad idea if you have very large data sets. Why is that a bad idea? Because it's difficult to understand as much things as in one go. Just think like you are a human preparing for an exams, and at the very time your lecturers give you maybe, I don't know, maybe 50 slides to prepare for the exam. So it's a lot. So what you want to do is like give it as like start by giving small examples and it learns on the go, not all at once. So it helps, it's beneficial in some way in terms of the learning process of your model. So once it sees little examples and it helps you generalize better at the end of the day. So how we can do this is what we call like batching. So we want to batch our data. Let's say we have this data set of 50K images. Then we can divide those data. So we can divide those data into like chunks. So each of the chunk, we call it a batch, and we can specify what is the size of that batch. So here, what we are trying to say, we want a batch of size 32. So at every instance of the model, yes. So at every time we want to train the model, so let's say we have this model here. So at any time we want to train the model, so we have like a batch of 32 images that is coming to our model, and it makes some prediction, and our model like learns from what it has predicted and tries to improve. So that's how like batching works, or batch size. So after it has predicted on those tattoo images, the next set of tattoo images comes in, and until we are done with the entire batch of like 60K images. So that's the idea of batch size. And you can set this to any number you want, so as much as you want. So, and one of the general practice is to start with like batch size of 32, depending on how your model learns. So if the learning is quite slow, then you increase the batch size as appropriate as possible. So you can experiment with this number. So feel free to experiment with this number. And there's a famous quote by Jan LeCun about maybe 8 years ago that friends don't let friends use batch size greater than 32, something like that. So batch size of 32, it's quite a good number for a starting point. So what this train loader does, it creates an iterable for us. So with this batch size we have intended, which we set here. And if you want, you can shuffle the data sets. So it's not like as the data set comes, so it's like some random assignment or some random picking of the data set. So that at least when you look through the data, at every looping, you get like, maybe this first data is maybe 32, 32, 32, 32. Then your 32 won't go on forever since it's like, let's say 60K images. Then at the very last, maybe you could get something like probably 18 or something. So, but most times you have like 32 images, each of which like goes to your model at every like step or at every iteration of your model. So yes. So for your test set, you can also do that. We are setting a batch size of 32 here. And there's a quick question from Bello. How does the batch? So there's a question from Bello about like the batch. So how does it connect all your results from all the batches and decide whether there's improvement or not? So when you set the batch size, so at the end of the day, the aggregation is more of like the average results of your batch size. So let's say you run an example once and you on a batch and you get perhaps an accuracy of 98. That doesn't reflect the performance of the model on the data set. So you have to run it's more of like you are running all the data sets, but you are doing it in chunks. So you have to run all the examples all together. Then you kind of aggregate and do an average. Then you have like some like key metric based on all your data sets. Yes. So thanks so much for the question. So I will probably speed up a bit, but not so much, so that we can. So here we have our data set and we've set a loader for our data set. So now what we want to do is build the model. And in the last sections, we've seen how to build the model. So I think one key thing is mindful when you try to build these deep learning systems. So you have your data set and you want to build like a model to like handle those data sets. So what you want to know, what is important, you need to know what is the shape of that data that your model will see, just so that your model will be able to handle it. If not, with tensors, you get some errors, which you don't want at the end of the day. So first, what we want to do is check the shape of our data. We know what's going to our model, and we can work with that, which we'll do in a bit. Just give me a minute. Let me just plug my laptop. Yes, thank you. Yeah, so what we want to do now is get the shape of our data. And as you can see here, the shape of each example of our data is what? Is this 1 by 28 by 28? As you know, like it's an image, it's more of like either a square or a rectangle. But for this model we want to build like a linear model in which it has like a set of neurons here, and it has like it does some predictions. Then it does some predictions here. So what we want to do here is we have this square image of 28 by 28. So, but we want it flattened. But I'll explain why this is not a good idea. So we want it flattened. So 28 by 28, what you have is 484. So this is like a naive way of doing deep learning on images. And this is what people have tried before the advent of convolutional neural network. So you have an image and you kind of flatten it out and you have everything like in one particular dimension and you pass it to your neural network. So what your neural network sees is just one dimension. So imagine how you see what, like the image of me, how you see now. So imagine from the top, you cut it across, everything across, and everything is just like in one straight line of several images. Then you pass it to your model. But that causes a huge problem. And we'll come to see why that is and how we get to resolve that with convolutional neural networks. So firstly, let's create our model. And if you have any confusions, feel free to ask your questions on the chat. So here, as we explained, we are trying to build a model. So I won't go deep into what it is. So I'll only explain this. So what this does is nn.flatten. So this comes from touch.nn. So it's a neural network model from Touch. So it has like several components. One of the components is this nn.flatten. So any input that nn.flatten sees, it converts it into one dimension. So imagine our image of, let's say 28 by 28 here. So when it comes into the nn.flatten, so it kind of levels everything down. So it becomes like this. So instead of the square, it becomes like a line. So it's like just one dimension. So we have 28 times 28, we have like 784 pixels along one dimension. So that's the idea of nn.flatten. So we'll come to see why the flattening is a bad idea or not so good. There's something better. So once we have flattened, what we want to do is pass the image into two layers. So which is like linear layers, which we've explained in last class. And we have an output. So like I said, be mindful of the input that's coming to the model and the output you're expecting. So if you remember, for our model, what we want is our image shape here is 28 by 28. And you have your model. So at the end of the day, what we want the model to predict like 10 classes. Like this, maybe, is it boots? Is it cap? I'm not sure if cap is there. Is it a shirt? So 10 classes. And each of these classes, it assigns like a probability to which is the best or which is as predicted. So in the input to our model is this. And we know it's like 28 by 28, which is the input shape. So because of this flattening, it will flatten it to 784. Then the output is what we want to predict at the end of the day. So it has 10 classes. So the output of the model will be predicting like 10 items. So, and each item will hold like part of the probability whether it is the item or not, which you will come to see. Don't worry, we'll get into it. So there's a question by Tenimu. There are no hidden layers. So yes, not really. So there are hidden layers. So because I think one of the notations might be misleading for deep learning. So this hidden unit here would mean like the hidden layer. Or you can say this here entirely would be the hidden layer itself. So it depends on the notation you are using for the like deep learning. So you can just call this the input or the hidden layer. And yeah. So this is like the very naive model we can build, but we'll come to see how that works. Then we set everything up similar to what we did in the last class, where you have, so these are just additional. So let's go to where you get to train the model. This is evaluation. So, but don't worry, when you get to see this, you will get, okay, can I see? Okay. Just give me a minute. Yes. So here you can see how the training has happened. And you can see in the very first epoch. So if you don't know, epoch is, so epoch means like going through your entire example. So here we have 60,000 images for the train set. So one epoch means we have gone through all the, let's say, training data set. So that's one epoch. So we've seen the data set, the entire data set one time. So when we go like epoch 2, that means we've seen it 2 times, and you can go multiple times as much as you want. But you don't want to go too much, because that leads to overfitting. That means your model is just memorizing the data set. So you can see at the very first epoch, you have a loss of 0.47. Then at the last one, it like goes down to 0.45, which is good. It's going down, but it's not as much as like we would have loved it to be. We want it to be lower than that. So as you know, like the loss, we want it to be as close to 0 as possible, both for the train and the test set. So here we are just monitoring the train loss. Then later on, you see how, so here I'm very sure the test loss won't be as good as the training loss, because it's just a very naive way of doing it. So I would skip, because for the sake of time, I'll skip this. So next step is like adding linearity. So I'll just skip to the part where we get to use convolutional neural networks, and just for the sake of time, and explain what it is, what it does. Just skip this also. These are mostly like helper functions, and yeah. Yeah. So yeah, so you've seen like how we could do it naively with just linear layers, and you get some loss values which are good but not so good, because we want it to be as close as 0. But you come to see like with convolutional neural network, it's better. So how will let me just explain it quickly to you. Okay. So, okay, let's look at this image one more time. So here in this image, I kind of shared the idea of how pixels work. So let's say we divide this image into maybe, okay, just give me a moment. Let's say we divide this image into this form. So here, what happens is, let's say each of this is a pixel. So normally when you try to see an image, how would you see an image? You see it as a whole or some part of the image. So here, if you want to identify a cat, you don't need, just looking at this. So imagine you can just see this pixel alone. Let's say this pixel here. Imagine you are looking at this pixel alone. So it can give you an idea like it's a cat, but it doesn't give you sufficient information as a cat. You need to look at like all the pixels around it. So with convolutional neural nets, what we were doing before with linear layers alone, what we were doing is like looking at this individually, looking at this also individually, looking at this individually, looking at this individually, which is like a really bad idea, even for a human, because once you begin to look at the images in between, so it takes a while for you to truly identify, like, let me just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So once you look at like number 6 alone, try to blow out everything else. So it's difficult. You might have an idea, maybe this might be a cat or this might be a tiger even. So you have to look at like other pixels around it, like perhaps 7, 8, and 9. So that you get a better idea, like this is actually a cat. So, but when you are dealing with linear layers, so how it does it is look at them like individually as like different like features itself. They are independent of one another. So it's a bit difficult to identify a cat as it is. But here, the beauty of convolution is it has what we call like filters, which is like we can say a filter, something like this. So a filter is just more of like an array of numbers. Let me see a filter of, let's say we have a filter of 2 by 2. So what happens is this filter goes across the image. It's 2 by 2, so it goes across like two of this, just like an intuitive explanation. So this filter goes around, like, let's say for the very first step, it goes around pixel 1, 2, and 5, and look at what's within that pixel itself. Then after looking at pixel 1, 2, and 5, that's in the very first, maybe, let me just say iteration. Maybe let's say I is equal to 1. Then next it goes to pixel 2, 3, and 4. So it's having like some idea of other pixels around. So not just one pixel. So it uses the concept of like locality. So within a particular location, what is like the contribution of other pixels? Then hopefully when it gets to this particular center here, 6, 7, 10, and 11, so it has better idea because you can see like this captures more of the face of the cat itself. Then it gets to understand this is actually a cat. But this is like a very naive explanation, but goes deeper than this. And the pixels are much more lower in dimensions than this. So there's a question by Aliyu. Some features might be hidden while flattened. Some features might be hidden while flattened. No. When you flatten the image, so it will still be as it is, like everything will still be like the way it is. So let's see how we divided this into, like this is okay, 14, 15, 16. So once we flatten this, it will be like an image. So this question from Ali, like once we flatten the image, will some features be missing? No, you still have everything as it is. So you still have like 0, 1, 2, 3, up till 16. So we still have everything. So if we use 1 by 1 filter to go, if the filter is 1 by 1, do we go back to linear? You don't really go back to, yeah, I can't see. Yeah, I can't say, no, you don't really go back to linear, even if you are using 1 by 1, but I'll confirm on that and get back to you because each of the kernels is going through the entire image, but if it's flattened, like each neuron will just see a part of the pixels. So let's say this is 16 by 16 and you have like neuron of 16. So here will come to this will come to this will come to this, and like this system will come to this. So it's a bit independent. But if it's convolution, it will still like go through the entire pixels of the image. But I'll confirm on this, Bello. Thanks for the question and get back to you. So quickly, I'll just skip to how we create the network so that you see it and you get to appreciate it. So yeah. So here, what we want to do is to build a convolutional neural network. So let me just run this, then tell you how it works about the model. So first, this model has like some blocks. So here, what we are telling it is, let me see. So it still follows the standard model. So I'll just explain one block and hopefully you get to use the idea for the subsequent block. So here in the block 1, let's say we have an image of 28 by 28. So maybe it's 3 by 3, let's assume, but it's 28 by 28. So first, what you have is this convolution 2D. What we are telling is to create a convolutional network for us, and we want to specify the filter. They call it either filter, or maybe you can call it like kernel. So what will go around this particular image that we have so that it will like look through the image? It's more of like a scanner to identify the features of this image. So we are telling it like we have a convolution and this is the input shape of our image and this is like the output, what's like the resulting. So what happens is this is our image and we want a resulting maybe kernel. Just give me 1 minute. So we want like some kind of result. So this can be like say 2 by, maybe this our image, assuming it's like 3 by 3. Then we want a corresponding result of 2 by or 3 by 2. This can be any number. So I'm just giving an example here. So here, what we are specifying in channels, I'm specifying the shape of my image. What's the shape of the image coming in? And at the end of the day, what is the number of channels that are going out at the end of the day? So I think this is it. So as we said, in the very first sense, we are dealing with RGB images, which is like 1 by 28 by 28. So which just has one channel. So here we can like transform it to some n channel of like maybe shape 6 by 6 or anything. So this n here can be any number. This is what you actually set here in this out channels. So from these channels, you want to make the model much more deeper. So then you set this n to any value you want. Then this kernel size here is the shape of this kernel. What do you want to loop over this image? So here we're specifying a kernel size of 3. So we want some kind of filter or matrix of size 3 by 3. When you said 3 here, so it means here you have size 3, and here also have like size 3. So this, think about this like a scanner that looks through the image as we explained, just to search for like relevant features and activate them as you go. Then this stride here just means, can you just give me a minute? Let me just make the image larger just so that we can visualize it better. So this stride just means like what is the movement pattern across that image. So imagine this kernel or this filter, or assuming this scanner that we're talking about comes here. It's looking at this size of the image 3 by 3 here. So it's occupying this space. And we have set the stride to what? 1. So what happens in the next step after looking at this first 3 this pixels at the top left? So in the next step, it will move like 1 step forward. That's the effect of the stride. And to look at like the next one here. So it has just moved like 1 step forward. So you can see then in the very next one, then to move like 1 more step forward, and it's looking at like the next pixels towards the right. So that's what it does. So that's like basically the idea of convolutions. So you kind of look through the image and you're kind of scanning for patterns. So, but this is just like an intuitive explanation. You just get you started about it. So then here we add activations. So in the last class, you saw the effects of activations, and you have like some kind of another extra convolutions of the same size of the kernel size, and it's moving like 1 step at a time across the image. So I'll just clear this and run this. And so you can see it has like first block, second block, and like the classifier at the end. So remember we said it's always good to visualize what's the input and what's like going out of your model. So at the end of the day, after you've had like these convolutions, so you'll be like left with some resulting matrix of perhaps this shape. So what you want to do is apply like flatten. So you want it to be in a 2D shape. So it becomes in your regular 2D shape after applying those convolutions. So, and you can pass it to some linear layer, which classifies it, and you get your prediction at the end of the day. So that is where this comes in. So the output for the convolutions, you flatten it, it becomes like in 1 dimension, and you apply these linear layers to make the predictions for you. So the general idea of convolution is the idea of locality. So it's not looking at just one pixel independently. So it's looking at like entire area of pixels so that it can get to derive what patterns. And so, for example, when looking at the human face, so you can see like let's see, the eyebrow here has a pattern. So with convolution, it helps to identify those patterns. So after you've identified those patterns like internally, so at the end of the day, you use your linear classifier to classify it into the number of classes you have. So generally after like setting out your model, then you have this forward. It goes into like the first block of convolutions, second block of convolutions, and your classifier to predict the output of the image for you. So let's run this. I think we have then see how it works, but I would, yes. So I'll definitely advise, Yeah, you can have a view about this and see. I believe like there's a GitHub link here, but if not, I'll share it, which kind of goes into better visualization of the convolutions. So I guess just have like an intuition of how this works. Then you don't need to go really deep into the maths for now. Just learn and appreciate it. So at the end of the day, later on, you get to see how it works. So let's try to see how we can train this model in which we have and see how it goes. So you can run this and see how, let me see, just give me a minute. Yeah, let me just run this and see where it trends. So this just explains like the convolution, what we've explained, and get some numbers. So here we just want to train and see the results. It will just take about some few minutes. But in the meantime, feel free to ask any questions that you might have. There's a question by Bello. So is there overlapping in the case the kernel size is not a factor of the bigger matrix? Yes, there will be overlapping. Yeah, there would be overlapping based on how you set the stride. So imagine, let's say you have an image. Let's say this image here, let's say 3 by 3, and you have a kernel of maybe size 2. So you see, this is not a factor of the original image because the original image is 3 by 3 and this kernel is like 2 by 2. Then first it goes here. So what is important is how you set your stride. So if you set your stride in, yeah, so if you set, just give me 1 minute to accept this. So if you set your stride to a very big number or a bigger number, so it kind of skips the overlapping. But in some sense, you really want the overlapping at the end of the day. Yes. So yeah. So let's just see our results and yeah. Yeah. So you can see for the model results we have here. So it's significantly better. If you remember in the last result, let me see. Okay, let me just join again. So in the last result, we have like 0.45 in the training loss. Yes, so we had like 0.45, but you can see here it's much more lower because with the effect of convolutions, so it's trying to learn some internal representations of the model. So can we have more than 2 blocks in the convolution? Yes, you can have more than 2 blocks in the convolution, but you must be mindful of the size of your input image. So just give me a minute. Let me see. I'm coming, I'll share in a moment. Yeah. So yes, so there's a question from, so there's a question from, yeah, can we have more than 2 blocks by Tanimu? Yes, you can have more than 2 blocks, but the issue is, let's say you have an image, or let's say you have an image here. So when you apply convolution, so it's either the size of the next feature map remains the same or becomes smaller and smaller and smaller at the end of the day. So it has some level of like how low it can go. So you have to be mindful about that at the end of the day. So I guess there are, so but you can see here, like when you try to deal with like locality of the image, you have better on this, your model tries to learns better than just looking at just one instance of the pixels completely. So yes, so there's also another follow-up question. If yes, can that improve the performance of the model. So when you, this is like a very small image of 28 by 28. So, but when you deal with like very large images of maybe 256 by 256, then you can apply as much convolutional layers as you want. So, but for this is small, so you have to be mindful so that it wouldn't be an overkill, because with the convolutions, you're adding more parameters to your model. So with more parameters, you have to make sure you have sufficient data for a model to learn, and also then train it for longer so that it learns like the underlying representations of the model. So yeah, so this is like the major high points of the lecture. So this is, and yes. So here in this particular lecture, you got to understand what is like, what is computer vision, or how computer vision is important. And you saw the different tasks, and you saw the importance of having convolutional neural networks. But this convolutional neural network in which you get to see, this is like a very simple and naive convolutional neural network which works, but there have been like various variations over the years. And as you can see, like there are ResNet, there are AlexNet, and several other variations which have utilized different variations of this CNNs and have improved upon it. So one of the projects we had last year had people use like this particular network, ResNet, for real world scenarios, and they learned to utilize it really well. So hopefully with what you've learned, it will be getting you prepared for the next, for the coursework project in which you'll be doing in perhaps a month or two, hopefully. So, but feel free, I know it might be some kind of new topics for a number of you, but feel free if you have any questions or concerns, just you can either raise them now or on the chat at any point in time. So that's majorly, I'll just wait for a minute if there are questions. Yeah, so there is a comment about assignment feedback by Tanim Abdullah. Yeah, thank you for raising that. So if you have any challenges, just feel free to email this email. So if you haven't gotten your feedback on any of the assessments, please just email us. We'll look at it. So probably some oversight, and we'll get it sorted out as soon as possible. Then, yeah, and also like, please try to submit the assignments. So I know the deadlines are like really fast approaching. So we had like an assignment for classification. Also submit that as much as possible, because it affects how you get certification and help us gauge your learning, or how well you are learning at the end of the day. So there is a quick question from Bello. If we use batches, where is the power of parallelism? Okay, I'll quickly explain this, then we call it a day. Yeah, come in 1 minute. So there's question form, which is like a good question. So I can't seem to take this off my screen. So there's question from Bello. If we use batches, where is the power of parallelism, which is like really good. So assuming you have this large data as we have, let's say you have data 1, you have data 2, and you have perhaps data 3 here. So this is maybe out of our 60K data that we have, still using the example we had all along. This can be 20K, this can be another 20K, 20K. So ideally how it should happen, this data comes in batches. Maybe you have, give me 1 minute. So you have your model here, and you have each of these like coming in, this goes in and it finishes, this goes in and it finishes, this goes in and it finishes. So normally it should take maybe ×3 of the normal time taken to like use just one data batch. But you can do it in such a way, if you have like several GPUs or maybe several parallelism. So you can, let's say you have, maybe you are blessed with several GPUs. Maybe your GPU 0, you have a copy of the model, and let's say your GPU 1, you have the same model. Then you have another GPU, you have another copy of the model. So what you can do is easily maybe passing to GPU 1, passing data, the first data, GPU, the second GPU passing the second data, and the third GPU passing the third data set. So this is where you are leveraging the power of what we call data parallelism. So you divide the data set, and each chunk of the data set is situated in or is passed to one some to the model, and the model resides on like one accelerator or GPU. So this takes like 1/3 of the time theoretically than using this particular approach where all your data goes to one GPU. So that also goes to the idea of batching. So usually what they call it is either micro batching or batch by device. So you can have like some global batch size, and for each device, it says like some kind of batch. So this is where like the power of parallelism goes for when you use batching. Yeah. So I hope it answers your question, Bello. Yeah. So yeah. So thanks so much for the questions and comments. But I know like this might be complex. Then if there's anything, just message us on the Discord or email. We are happy to like answer your questions anytime. So thanks so much, and hope you have a wonderful rest of the weekend, inshallah. Mm. Yeah, thank you. Yeah, always welcome. Bye.